this formula is for the chain rule in partial derivative where the function has 3 independent variables. So that means W is in terms of some x, y, and z. And then each x, y, and z is in terms of t. I will be using this example that W is equals to ln square root of 3 independent variables, x squared plus y squared plus z squared. W is a dependent variable. The value of W depends on x, y, and z. And then each independent variable, x, y, and z, is in t. Okay, x is sine t, y is cosine of t, z is tangent of t. How do we do the partial derivative? Let's do a quick review on the 2 independent variable where z is in terms of x and y. So the derivative of z with respect to t, we have 2 pieces. One for x, one for y. Within the x, we do the partial derivative with respect to x, and then immediately we take care of the x with respect to t. Take care of the x means we take the derivative of x. And then plus the partial derivative with respect to y, and then immediately we take care of the derivative of y with respect to t, and then we will expand this formula to 3 independent variables. So that will be dw dt, the derivative of w with respect to t. Okay, where is the t? T is right here. One in x, one in y, one in z, right? So we will take the partial derivative of w with respect to x, and then immediately we take the derivative of x with respect to t. So this is the entire piece is for x, and then what we multiply is the derivative of x with respect to t. So since there is another variable t in x, we will also have to take care the derivative of x with respect to t. So that's why this is a chain rule. So the chain is actually right here. And then plus partial derivative with respect to y, and then we take care of the y with respect to t, plus the partial derivative of w with respect to z, and then we take care of the z immediately for t. So basically there are 3 pieces. We add them all. One for x, one for y, one for z, and then for each piece, we start with a partial derivative with respect to that, and then we immediately multiply the derivative of that variable with respect to t. All right, so for the green problem I provided below, let's do you see that there is a ln, there is a square root. So the square root means x plus y plus z squared, okay, is raised to half power. So the properties of ln allows me to bring the half power in front of ln. So that will make my life so much easier. I will just rewrite the function a little bit before taking the partial derivative. Okay, let's do it. This is going to be long. So we are taking the derivative of w with respect to t. So let's take care of the x first. So that will be partial derivative with respect to x. And then immediately, oh, you know what? I will just do it instead of like replicate the formula one more time. Okay, partial derivative with respect to x. So that will be the ln. The ln is always 1 over the entire thing. So we have 1 divided by the 2 is there. So that will be the entire thing, x squared plus y squared plus z squared. And then what's inside the parenthesis, I will take the derivative with respect to x, because we are not done yet. So the partial derivative with respect to x is not done yet because there is a little chain rule in here. So we have a chain rule inside another chain rule. So other than taking care of the ln, I also need to take the derivative of what is inside, which is x squared plus y squared plus z squared with respect to what? With respect to x. This x, we are still on the partial derivative, okay, with respect to x. So that will be 2x, and then the y, the z are all constant. You know what? I will just keep the 0 and a 0. It is easier for me to, when I go back to read what I just did. So now we multiply. We multiply. We are doing this multiply. The derivative of x with respect to t, which is the sine. The derivative of sine is equals to cosine of t. Okay, the first part is done. And then we do a big plus, and then moving on to the next piece. So the next piece will be, and then we still bring the whole thing to the denominator, so 2, and then x squared plus y squared plus z squared. If you want to save some space, when you do the chain rule for this, x squared plus y squared plus z squared with respect to y, because with respect to y, we are right here. Check, follow my cursor. We are right here with respect to y. okay, with respect to y. So the derivative of y squared is 2y. This is a 0. This is a 0. You know what? You can just write 0, the derivative of x squared, and then for y, and then for z. So you can save a little bit of space, and then you multiply. Now we are doing this, dy dt. Derivative of y with respect to cosine, that is negative sign. So negative sine of t. So now for x is done, for y is done, we are moving on to for z. And then we do a big plus. For z, same thing. We take care of the ln. We bring the whole thing to downstairs. X squared plus y squared plus z squared. And then the derivative of this, we are still working on the partial derivative. So this time only z squared is a variable. So the x is 0, the y is 0, the z squared is a 2z. And then we multiply this dz dt. So that will be the derivative of tangent, which is what? Secant square t. And then you have to clean this up. Do they share anything in common? Yup, they do. So dw dt, they share the denominator in common. And then what else can I do? You know what? Here, I can actually reduce the 2, right? I can actually reduce the 2. Okay, so the bottom will be x squared plus y squared plus z squared. And then the top, that would be the first one, I have a x times cosine. And then a plus. You know what? The sign has a negative. So instead of adding a negative, I will just do a minus. So that will be a minus y sine of t. And then the very last one, plus z secant square of t. That's it. So that is the chain rule for partial derivative, where w is in terms of 3 independent variables. So as always, we do one part for x, one for y, one for z, and then within each part, we take the partial derivative. So we do partial, just make it simple. We do partial with respect to that variable, and then immediately we take care of that variable with respect to z. We will just do this for each independent variable. So now, even though there are 4 or 5 or 6 independent variables, you can just follow this concept to expand the formula. So for 5 or 6 or even 7 independent variables can be done easily, just a matter of time. All right, so that is the end of this video. If you like my explanation, the way I explain calculus, subscribe to my channel, give the video a thumbs up, and I will meet you all in the next one. Signing out.